Welcome to my YouTube channel Time Sector. So today in this lecture we discuss the one of the first model is model agnostic method in accumulated local effects means ALE. So in this lecture we discuss the complete. If you not watch the previous lecture in PDP and IC, then please go through those lectures so you easily understand the more better understanding of accumulated local effects. So if you are first time on this channel, please do the like, share and press the bell icon. So when we will upload a new video, so you will get a notification. So today in this lecture, we discuss the accumulated local effect. So what is the accumulated local effects, right? So in that case, uh, this model shows the features affect model predictions, but they solve the problem of PDP, right? Accumulated local effects solve the problem of the PDP, right? So in the PDP doesn't depend on the each other. So let's suppose X1 features and X2 in the PDP not depend on each other, right? Not depend each other. Unlike PDP, ALA looks at how predictions change locally, right? When a feature change, so capture interactions between features, right? This is main object of AI. AI can be local or global. I already explained in the first lecture what is the local and what is the global. Depending on how much data you can combine when summarize the result, right? So this is simple. So now we have one questions. How we plot AI, right? So first we split a feature like in bins, right? Break the feature value into a small interval is called bins, right? Then find the local changes. In each bin, change how prediction change when the features goes to the start and end of the bins. I will explain in the order. If other fixes only move to the chosen features, like if we choose the x1, then go with x1. If we choose x2, then go with x2, right? For other features are the same, right? One is the changes and other are same. And let's suppose we have x1 features, x2, x3, and x4, right? If we choose x1, then this all features are the same, right? Then add up changes. Accumulated, it means the sum of features, right? Local changes across bins. So we will see the overall effect of the features. Then the plot of the result in x-axis, the features value. On the y-axis, the centered, you can easily compare the impact of the features, right? So now I will try to explain the detailed logic of ALE prods. So in that case, first, so in that case, I will try to explain the detailed logic of ALE prod. So first we will make a data set. Suppose we make it 20 rows. In that case, we make it 25 rows, right? 25 rows with two features. We have two features, x1 and x2. And we have target is y, right? So in the x1, it goes from 0 to 25, but in the features x2 goes from 10 down to 1, right? The range between 0 to 10, right? And then we train the model. Again, we use here is decision tree regression, not a classify regression, to learn the how x1 and x2 predicted y, right? And shows the features. Let here we shows the features x1, so could also do x2, right? So now we split into bins, right? This is the bins x1 and split in the bins, right? then calculate the local effect. And clearly we calculate local and global both, but here we calculate the local effect. So for each bin, make two versions of dataset. First, x1 set the lower is the bins and x1 set the upper is of the bins. So run the model on both version in lower and upper, right? Then these average these difference the give the yearly effect for that means on the bins, right? Then accumulated effect add up to the local effect across being stabilized. For the result, x-axis midpoint of the beans and y-axis. This is my y-axis is means target. This is my y, right? This is my target, right? And this is my x1 is the my features, right? Features. And this is my bin size, right? Bin size, right? So what is the solving this plot? Now we discuss, right? We have we have 20 rows, right? And with respect to the two features. So in that case, add the first. This is to this is add the first. The plot is the flat, right? So in that case, the meaning of x1 doesn't affect the features, right? On the prediction much. But after the this point to this point, this point to this point, this line, so I will try to sense the pen. So this point to this point, x value is increasing, right? Increase, right? So in that case, the line is rise sharply, right? So showing that as x1 is increased, the model predict a higher value of y means target, right? After that point, so so on that point to that point, the line is decreasing, right? Line is decreasing. So line is drop to in that case, indicating that drop beyond a certain point, right? So increasing H1 actually reduce the prediction, right? So this is my X1, this is my means, and this is my Y, this is my target, and this is the my features. And I already explained in the notebook, so we go through the notebook. Now we discuss the what to look for in AI, right? So first we look at the shape, right? We look at the shape. The if line is straight, then this is the my linear. If the curve non-linear and the flat for some parts, and in that case, this line is flat, right? So flat part means the features are not really changing the prediction there, right? Here, here is my line is the flat, so here is the my prediction is the not change, right? So there and jump or sharp changes, right? So palace where the features suddenly start to matter one. So here we observe, normally here we will observe this line is increase, right? So uh, in that case, hint at interaction with other features, right? This line is increase, this line is decrease, decrease, this line is flat, right? And now compare with the PD. In the PD, if ALE and PD look different, so it usually means the features is correlated with the other feature. So what is the problem in PDP? PDP in if the features is highly correlated, then PDP is not useful. But in the ALE, if the features are highly correlated, then ALE is useful, right? So this is, and PDP independence assumption is hiding that, right? So now assumptions of ALE. What is the assumptions? So in ALE, measured locally, so ALE looks at how the features affects prediction on small neighborhood, right? So assuming nearby value makes sense, right? And bin size is more better, much better. So bin sizes matter. If if the bin size is too small, then prompt may capture random noise, means outfitting, right? If bin size is too large, so which may miss important interactions or detail. So we lose the values. Yeah, important information, right? So bins should be balanced. In the main role is really bin size is more important. So in that case, bin size should be balanced, right? So small enough to catch real pattern, but big enough to stay smooth or reliable. So when we will use the AI, right? If features are correlated, right? Or in fact, PDP assumptions of independent doesn't hold. So ALE is better, right? So already explained. So ALE lets you see both local effect or global effect. I already told. It gives more robust interpretability because respect feature dependencies. Right? Now, how ALE improve upon PDP? Right? So in PDP, assume features are independent, but in ALE, features are dependent and correlated. Doesn't matter, right? So ALE work better when features are correlated. In fact, because the respect those dependencies, right? PDP can create unrealistic data rows when ignore correlation, when really avoid the problem. And PDP shows the effect using global areas, global and local both. So ALE shows the effect using local senses bin by bin, then add them up. Right? So what is the limitation of ALE? So again, same problem is complexity. You need to choose the bin size carefully. If we are not choose and we not choose the balance size of the bins, then this is if too small, then knows the result. If too big, then miss details. Right? Harder to read. ELE can be trickier to interpret than predict. So in the PDP plot, we easily read, but ELE plot, we easily not interpret, right? So especially if the model is very non-linear, but in that case, we easily understand. But if the non-linear, then we cannot easily interpret, right? So so in that case, again, this really depends on how finally you split the bins, more details, right? But also more risk for the noise, right? So what is the focus of AI, right? What is the exact goal of AI? So global view, the full AI curve shows the overall big picture effects of the features, right? We have two features. So local view, when we are using the local view and when we are using the global view, right? But global view shows the overall picture, big picture, right? But local view for each means, let's suppose we have this means 2 and 4 only for show this means, right? So a small sense in the predictions, we saw the local effect. And model agnostic, ALE work with any model types. Again, ALE, PDP, and IC all are working with any models, just like PDP and IC, right? Because it doesn't depend on how the model is built inside, right? I already explained in the first lecture what is the model agnostic terminology, right? Now we discuss the difference between the ALE, PDP, and IC. Right. So in the first point is feature dependency. Right. So in the ALE, consider how features interact by checking local prediction senses, but in the PDP, features work independently, and average there the effect of the features. But in the IC case, PDP like PDP but shows effect for each individual data points, not average, right? So in that case, focus combine small local effects into one overall curve in yearly, but in the PDP, only the overall global average effect, right? But in the IC case, focus on each instance local effect, right? Third is the plot output, right? One curve showing accumulated local effect, right? Simple. But in the PDP, one curve showing average effect across all the data, right? But in the same case of the IC, many curve, one for each data instance, मतलब it means individual. So for this point, when we use the ALE, PDP, and IC, so when features are related or interact with each other, means correlated. So in that case, we use the ALE, right? When features are independent or you just need to overall, when we will check the overall data. So in that case, we use the PDB. So when we will use the IC, right? So when you want to see how each instance behave differently, right? So in that case, for individual, we use the IC. So now we go on the code. So again, uh, um, check the IC plot, PDP, and ESC. So first, again, same data set. Already we discussed, we have the 25, right? 25 is x1 and x2 is again 25 and y is the target. We have two features and one is the target. Again, show the data frame and train the models. We go through the decision tree, regressor, not use the classifier. So again, partial dependence plot. Here is the partial dependence plot for the respect to the features x1, right? So average of the features, right? And again generate with the features with respect to the x2, the PDP plot. In that case, plot is decreasing, and again together both the IC and PDP plot with the features x1 and x2. Then we go through the individual conditional. So in that case, all individual plot with respect to the features x1, and in that case, we go through the features x2 for individual. Now we discuss the accumulated local effects, right? So here we define the ALE plot. In the ALE plot, we have the four parameters: is base estimator, x, and features name, and features name is string, and bin size is 4, right? So this is the parameter. Bins number is split the feature value into bins. And here is the 4. Size of bins is 4. So generate it for the given features. We have the 4 parameters: model, trained machine learning model, which model we will use, and X is the data set on the features X1 and X2, and features name, more data set, and features name, the features to analyze, which features we will analyze x1, x2, and bin size, number of bins to split the features value into, right? So now extract the value of the features we are interested in, right? Features x value and x2. So here is the my x and value set. So define the bins for the features. Bin is np line space, right? And minimum size and maximum size and bins plus one, right? So we already store the yearly values and yearly values and bin centers too. And now we go through the loop for each bins for I in the range bins, and we already bounds to lower bounds and upper bound, right? In upper lower bounds for I and upper bound for I plus 1. Then again we do modify for feature value fits the bins boundaries. So we do the copy. So X copy for the lower bound, X copy and X copy for upper bound, and again copy, right? Then replace the value of the features. So bin boundaries. So features name and feature bound again same, right? Then we do the predict, right? Copy. Then calculate the difference in the predictions. Here we predictions, right? So yearly difference is NP mean of Y predicted upper, Y predicted the lower bound, right? Because we already explained. And now explain the yearly difference and page center. So yearly values append yearly difference. We already find here the yearly difference append. Then bin center append lower bound plus upper bound divided by 2. Right? Now we will show the plot. So figure size already 8 and 6, and bin center yearly values marker is O, small o, and line size is dotted and color is blue, right? Title for yearly, a plot for the features with respect to the X1, right? And bin size and Y label is the target, right? Effect of on the model predictions, and grade is true. So here we have so the model. Model is the decision tree already, and X is the view of the data set. We have 20 size 26 and 2 means we have 2 features and 26 columns, right? And bin size is 4, and here we choose the features x1, right? Now we show the yearly plot, and this is my x1 features and split in the bins, 4 bins, and here is the my target, so effect on the model prediction, and this is my yearly plot. So here is my plot as the flat and increase and decrease, right? So again we show with the x2 features in the x2 fast decrease, increase and increase, right? So there is my complete plot of the IC plot, so yearly plot, and this is my end of the lecture. Thank you for watching this lecture.